So we will start our session in next 2 to 3 minutes. We will wait for other students to join and then we will start. Okay. I hope I'm audible there. Am I audible now? Okay. So, good evening. I'm Prashil. I'm a Prime Minister's Research Fellow at IIT Bombay. And here we are learning Advanced Thermodynamics and Molecular Simulations, right? Which is a postgraduate level course where we'll be using undergraduate thermodynamics and we are applying some mathematical principles to see how we can represent the systems using the concepts of statistical uh, thermodynamics, right? So, as we know, this is an advanced course. So, what we learn in undergraduate thermodynamics, it was, for example, I'm having a beaker, and this beaker has some water, correct? So, in undergraduate thermodynamics, we studied that this is a system which is exchanging, which is exchanging what? Heat, that is energy with the surrounding, because this system is open system, correct? This system is open system. This system is also exchanging mass with the system, right? So there is a energy transfer and there is mass transfer, and if such system is there, in that case we are calling that system as open system, right? To give you again a simple example, if I just cover this, if I cover this system with some rigid wall like this, right, and again it has some water, can you relate? I'm having a rigid wall, and inside that rigid wall, right, there is some fluid. In real life also we see, for example, it could be water, it could be any fluid, right? So in this system what is happening, in this system what is happening, there is no exchange of mass, right, because the walls are rigid, right? So no exchange of mass, and there might be exchange of energy depending on wall. If it is a dithermal wall, that means it can exchange the energy. If it is an isolated, if it is not exchanging any energy with the surrounding, that is called as isolated system, right? So in that case, this wall is not exchanging energy with the surrounding, and that's why it would be no exchange of energy, right? In other case, if there is exchange of energy, if there is exchange of energy, right, then we can say, okay, this system is a closed system where there is exchange of energy but no exchange of mass, no exchange of mass. Depending on the wall we can define multiple systems, right? So can I write this system, for example, I'm removing this, I'm just saying, okay, the wall is dithermal, which is exchanging the energy with the surrounding, but it is not porous, right? This is not allowing molecules to go out, and that's why there is no exchange of mass. For example, if you can see, I don't know, this is a Coke bottle, right? So what is there? This is a bottle and it has some liquid in it, right? It has some liquid in it. So this represents what I have drawn over here. So this is my bottle, right? It is completely packed. It has coke inside, right? So what is happening, because the tap, because the system is not exchanging, the tap is closed, right? The tap is closed over the top, and because of which no exchange of mass that is happening, right? There is no exchange of mass, only there is exchange of energy because the material is made up of plastic, right? So that represents, so this system that I had shown, that represents a closed system where number of molecules are not changing, that means n is constant. Second thing is, volume of the system is not changing. Is the volume of bottle changing that I had shown? No, it is not changing at room temperature, that means volume is also constant, correct? It is exchanging, it is exchanging energy with the surrounding, right? So if I am taking this coke bottle out of freezer, what will happen? This will exchange the energy with the surrounding, correct? And the temperature of the fluid that is present inside this bottle will come to the room temperature, that means it is exchanging the energy. So if it is exchanging the energy and if it is coming at the equilibrium, what is something that is constant that we know from the zeroth law? It is the temperature. When I exchange the energy, there will be constant temperature between these two systems, right? So in that case, energy is changing, and that's why temperature is constant. So in process control you must have studied, right? whenever i am controlling something Whenever I am controlling something, those are my controlled variables, right? Controlled variables. So what I am controlling here, I am controlling number of molecules. I want the molecules should not escape the bottle. I want volume to be the constant, and I want the temperature should be constant. So if I am controlling these things, that means it is NVT system. These are my controlled variables, which are also called as natural variables. So what we did just now in our 12th standard in undergraduate studies, we studied that a system, just like what I had shown, right? There is a bottle and inside that there is a coke, correct? The material is made up of plastic, it is exchanging the energy, and such sort of systems are called as closed system, where there is energy exchange but no mass exchange. Right now we are defining similar systems as NVT systems. So we had given a mathematical description, right? Whenever I am saying, okay, if the molecules are not exchanging, that means mathematically delta n is equals to 0, number of molecules are not going out of the bottle. Whenever I'm saying volume is constant, delta v is equals to 0, that means volume change is 0. Whenever I'm saying temperature is constant, delta t is equal to 0. So I had given a mathematical touch to whatever we studied, right? We have given a mathematical touch to whatever we are studying, and hence here it's an applied one where mathematics is being used to represent the system, and computers will be used to simulate the properties of material which is present in the system. Similarly, what will be the case over here? Since it is a open system, there is exchange of energy, that means temperature is constant. There is exchange of mass, then what is constant? In equilibrium, I have a membrane over here, and this is a mixture of CO2 and nitrogen. This membrane is allowing a sort of molecule, for example allowing nitrogen to pass or CO2 to pass. What will happen? There will be exchange of molecules from this compartment to this compartment, until what? Until the chemical potential is constant. right? So delta mu is equal to 0. That means until chemical potential is constant, there will be exchange of energy. And at equilibrium, obviously chemical potential in both the compartments is same. That means there is no exchange of molecule at macroscopic level, correct? Similarly, here there is an exchange of energy, and then exchange of energy will happen until the temperature is constant, correct? So delta mu is constant, delta t is constant, correct? And what else is constant? The material that is present. For example, if it is liquid, material is material exchange is happening, right? This is my system. Is the volume of system changing, right? So volume of system is not changing, correct? So in those system, depending on, see, in some cases it may happen that the volume may change, because for example this gaseous particle may go somewhere, so there is change in the volume of the reaction mixture that is present, but system volume is constant. System volume is constant. So in that case, delta v is equal to 0. So what is this system? Mu vt. So this open system here is called as mu vt. So what we are doing, we are just representing these things in mathematics, which will be useful for us to perform the theoretical calculations, to perform the computer simulations. Okay, so that we have covered. We briefly touched upon, okay, if this is the way we are representing it, then uh, what are different laws of thermodynamics, correct? We covered that part. We had used probabilistic, we had studied probabilistic approach. This will be useful for us in upcoming lectures, right, where everything is based on probability. If you are aware of probability of an event to happen, then you can comment on, okay, whether the system will go into that state or not, whether the system will come back or not, right? So those sort of things we had seen. Then I just need to look after my notes. Probability was there, and apart from that, yes, we saw what is entropy, right? And how entropy can be defined completely using probability, right? So S is equals to kb ln w, right? Kb ln w. So here in the zeroth law, we know temperature that we have defined. In the first law, we said, okay, energy is constant for an isolated system. And in third law, we went into the S, that is entropy. Entropy should not be constant, it should keep on increasing. Delta S should be greater than 0, correct, for any real process to happen. And then third thing is, what is the reference for that entropy? Because whenever I'm saying delta S, right, it is change value, right? So if I'm talking about change, there has to be some reference. From that reference I am going, correct? So that's why S reference. So these laws basically came one by one. We wanted to see, okay, why the temperature of a coke bottle that I have taken out will become room temperature after certain time, right? There is exchange of energy, because of it temperature is constant. That means my bottle and surrounding is in equilibrium. My bottle that I have taken out of the fridge and the surrounding temperature, those are in equilibrium. That is called as thermal equilibrium. So to understand why system exchange the energy and up to what it will exchange the energy, there was a need, and that's why zeroth law came into existence. We defined zeroth law. Then second thing is entropy. To exchange energy we wanted to define, right? For any system interaction between all particles that are present in the system, we wanted to define, okay, what is the capacity to do the work. If I am having a bigger system, it is having higher energy. If I'm having smaller system, I'm having lesser energy, right? That means based on that, based on the amount that is content that is present into the system, we wanted to see why certain system are able to do more work than some other systems, right? And that's where the origin of E came, right? And we came to know that when system and surroundings are being combined, we have delta U, that is change in the energy, which is equals to dW, right? And then this energy we define, right? And then we said, okay, energy is change in energy, that is constant whenever I'm going from one process to other process, right? So this is there. So for an isolated system, if the energy is not exchanged with the surrounding, right, that means some other property has to change. And what is that property? Because if there is no exchange, nothing is changing, then why the process should happen? There was a point why the process is happening if there is nothing that is changing, right? So to answer that question, it it came to know that, okay, there is something called as entropy that is changing and that governs the process to happen. Now in all the cases it was not feasible to say, okay, entropy, calculation of entropy, measurement of entropy, and check whether the entropy is changing or not, right? That's why we went into some other systems that we are going to see today, right? But again, as I said, this entropy is there. To define that change, we need some reference with respect to some initial location, and that's where the reference of the entropy we wanted. And here it came at minus 273 Kelvin. Entropy is equals to 0 for an isolated system. So these were the laws that we defined. Then we have represent those things using the probability, and we used probability approach to define equation of state ideal gas equation of state. So the concept of molecular simulation can be used to define the equation of state also. Then we had some example, coin toss example we saw, right? And there we found that, okay, if I am tossing two coins, I may get head, tail head, right? Or head tail and tail tail. And we have plotted what is fraction of heads versus probability, and we got to know, okay, for this probability is 0.25, for this probability is zero point 0.5, and for again this 0.25. So the distribution was looking like this. And we got to know, as I increase the number of coins, right, and if I plot fraction of heads versus probability of that event to happen, we got to know that, okay, overall probability decreases, but the probability overall probability for this event and for this event, right, here decrease in probability, but the probability of getting this center value, the distribution close to 50%, increased has increased. And we wanted to see, okay, what is that thing we by which we can compare these two systems. So we have to take this maximum value, here also we have to take this maximum value, right? And we have to divide all these probabilities by this maximum value. So you may compare those distributions and you will find that the distribution is becoming more and more narrower, and deviation from the mean value, that means most probable distribution, decreases with increasing n. As I'm increasing n, the number of events, these extreme events, will decrease, and we will be having most probable distribution, which is called as central limit theorem, right? Central limit theorem. Then the question that came into our mind was how the energy distribution happens in the system, correct? As I said, S is equals to kb ln w, kb ln w. So w is what? Number of ways in which I can distribute energy into the system. Number of ways in which I can distribute energy into the system. So we took an example that was for chocolate distribution, right? Let's say for example I have four chocolates, right? I have four chocolates and I want to distribute among three students. Three students. So what are the different ways in which I can distribute? For example, if I want one student to get two chocolates and the remaining will be distributed 1 1, so two students will get one chocolate each. So we had that formula, right? We have derived w, but instead of going in that way, I'll just give you with simple, I'll give you some simple examples. So this is my first student, second student, third student, and I want to distribute. What are the ways in which I can distribute? I can give two chocolate to this first student, one chocolate to second, and here this is the way. Other ways, I'll give two chocolates here, 1 1, and third one will be two chocolates to last student, and here 1 1. Is there any other way that is possible? Right? This is the way in which we can distribute. So how many ways in which I can give this distribution where one student is having two chocolates and rest two will have 1 1? Total number of chocolates is equals to how many? Four, correct? Into two, so this is four chocolates I am distributing. So there are three ways in which I can distribute. I can give two chocolates to first students and 1 1 to other, correct? And I can have this way also. So how to calculate these three ways? See here, we have drawn diagram and we understood okay how to distribute these chocolates. If I want this distribution, is it possible to do for all? For example, I have 100 chocolates or 200 chocolates. We cannot draw these things, right? We will say okay, 100 students will be given to one student, 100 chocolates will be given to one student, rest will not get anything, then 99 and distribute one among all 100 students, right? So drawing this will be very difficult, and that's why we came to know with the relation that w is equals to n factorial divided by n not factorial, n1 factorial, and so on. So what does this tells? N naught means number of students with zero chocolates. Here this is number of students with one chocolate, two chocolates, three chocolates, and so on. So for this system, can you calculate w? W for first system is n factorial, right? N factorial. So there are m chocolates. We wanted to divide among n students. So how many chocolates are there? Four chocolates we wanted to distribute among three students, right? So this is 3 factorial, right? And capital N stands for number of chocolates, right? How many students are there with zero chocolates? There is no student with zero chocolate, right? This is my distribution. So n0 is equal to 0. How many students are there with one chocolate? Two students are there with one chocolate, correct? So two students are there with one chocolate. Then how many students are there with two chocolates? Only one student is there with two chocolates, 1 factorial, right? And we do not have four chocolates and all, right? So By this logic you can see 3 into 2 divided by 2 into 1, so this is equal to 3. This is equal to 3. So using this formula we got to know how many ways are there in which I can distribute these chocolates. Similarly, can we have something else? I want i want 4 chocolates to be distributed in 3 students, such that one student will get 0 chocolate, correct? And if one student gets 0 chocolate, then I can distribute 2 2 or 3 1, right? And then I want, for example, 3 students with, just a minute, one student with 3 chocolates and one student with 1 chocolate, right? So 1 into 0 1 total is equal to 4. So can you calculate w for system 2 will be equal to 3 factorial divided by number of students with 0 chocolates is equals to 0, number of students with 1 chocolate is equals to 1, and number of students with 3 chocolates will be equal to 1. How many ways are there? This is the way. Am I making any mistake? Check it. 6 ways. There are 6 ways in which I can distribute this. You can draw these things, right? For this example also you can draw. You can give 3 chocolates here, then here it will not be there, right? This will not be there, and you exchange these things, right? Similarly, you give 3 here, then exchange first and last, so on, and you can get the actual value that there are 6 ways in which I can distribute. So what we did just now, we calculated W for a particular distribution. For first distribution we got W is equal to 3, and for second system W is equal to 6. So can you calculate entropy? S is equals to Kb ln W. If you just substitute the W, you will get to know that if W is high, S will be high, because this is log function, ln, right? So what we want a process to happen, we want, if the process to happen, the entropy change should be greater than 0. That means S2 should be greater than S1, correct? S2 should be greater than S1, right? That means if I go from system 1 to system 2, what is happening? S2 is greater than S1. That means I can go from state 1 to say state 2. It is a spontaneous process. But if I go opposite way, it is not possible. Why it is not possible? Because the entropy is decreasing. And how did I calculate? I calculate these things based on the W, right? For each distribution, for example, here this is the distribution. One student will have 2 chocolates, 2 students will have 1 chocolate. This is one distribution. This is second distribution. I can have multiple types of distribution, and for those distribution there will be corresponding W value, just like we did for two systems. And whichever the system will be having higher value of W is the most probable, and system will try to go into that W, that state, correct? So for example, I have a reaction that is happening where the reactants will go and convert into the product. correct? The reactants will go only when delta s is greater than 0. That means what is happening here in the product state, w is higher than w1. So based on the number of ways in which I am distributing something, that calculations, w can tell you okay whether the process is feasible or not. Whichever is having higher w will be a feasible thing. If I am saying okay w1 is greater than w2, that means this state, this is first state, this is my second state, w1 is higher, that means system will always try to go towards reactant state. And if it tries to go towards the reactant state, that means the reaction is not favorable, the reaction will not happen, right? So this w is something that is telling you the feasibility of process. Okay, so I'm just giving you few minutes to look after and understand, and then we can proceed with the next topic. Meanwhile, if you have any doubts, you can ask, that is also fine. So just like what I said, I have some chocolates I want to distribute among the students, right? When it comes to a molecular system, I have a system that has n number of molecules, right? And how do we calculate those numbers? We know if I'm having 1 mole of ideal gas which is present in a box, right? How many particles are there, how many molecules are there? There are Avogadro number of molecules, that is 6.023 10 raised to power 23. These many molecules are there, correct? And these molecules are there, and since I have a box, right, in that box they are interacting with each other. If it is an ideal gas, no interactions will be there. If it is a real gas, there will be some interactions, and based on that interaction there will be some energy. And total energy, we know it's the potential plus kinetic energy, correct? Potential plus kinetic energy. So I have kept those molecules in a box, and because of which I am applying some force, and I'm saying okay molecules, you should stay at that location, you should stay in this box. So applied forces are there, and if there are some molecules which are having attractive interactions, they will come closer together. If they are having repulsive interaction, they will go away from each other. Again, to give you an example, I have a bucket, I have added water over here, right? After certain time, what will happen? They will go to equilibrium, and there will be water which is present in the system, and the water layer is not moving, it is steady water. What I did at the start, I had randomly put water molecules, the layers were moving like this, right? If you just add water in bucket, there will be water which is distributed, but after a certain time it has become a water which is not moving, correct, which is not moving. Why that is happening? Because there is some attractions between water and water, and there will be some attraction between water and air, and there will be some interaction between water and the bucket surface, which could be polymer. So there are some interactions, right, because of which the total energy of system is coming, correct. So here I'm not applying I'm not applying anything, but I'm applying one thing. What is that thing I'm applying over here? I'm applying pressure, and that pressure is 1 atmosphere. Another thing that I'm applying is temperature, which is for example room temperature. So these are the things that I'm applying. Apart from that, there is nothing. So these are my applied forces, and under these applied forces this molecule is behaving, correct. Similarly, I have a box in which some gases are there. Because of the interaction between gas molecule, they may come closer together, just like this water molecule came, right? Or there might be some repulsive interaction. For example, I am having oil and water. So oil and water will not mix. Even if I mix, what will happen? They will separate. So this is the example. We are having oil and water, which is mix. Oil plus water mixture. What will happen at after a certain time? You know that they will separate. So there will be oil at the top and there will be water at the bottom. Correct? What I did, I had added everything together. I had mixed those things. Why the system is going like this? Why the system is moving into this state? Because just like I said, the W has changed, and W for this system is higher, right, than W for this system, right. Number of ways in which I can distribute the things is higher over here than here, correct. So this W is something that governs the process to happen, correct. So there are repulsive interactions here between, more or less repulsive interaction, okay. There are chances that oil or water, they may have some interactions over here at the interface where there is interfacial tension, but they will separate out. You will see some oil molecules in water and you will see some water molecules in oil, but right now we are saying okay, it is completely separating. So they do have repulsive interactions, and based on that they may come closer or they may go apart, right. Here water molecules came together because they have attractive interactions. Here oil and water separated because they have repulsive interactions, correct. So I have a box in which I have some chemical, right. There are molecules which are interacting, and those molecules when they interact, they have different energies, correct. And we are distributing energy into those molecules, just like what we distributed chocolates among the students. Similarly, I have my energy that I am distributing into particles. So can I give all the energy to only one particle? No. Can I give no energy to 50% of the particle and 50% are having something other value, right? It's not possible. That means there is a distribution of energy, just like distribution of chocolates. And which distribution will be more preferable? The distribution where W is highest, that is the preferable. And their distribution is something will look like this. This is the energy versus probability of having that energy. This is the mid average value where the energy is basically average energy, correct. Average energy, and average energy is calculated by this divided by number of molecules, correct. So I'm just saying this is the average value. So we see that particles with zero energy is less likely, and particle with all particles with high energy is also highly unlikely, and most of the particle will have this average distribution where all the molecules will have some distribution which is close to equal distribution. I am not saying exact equal distribution, I am saying this is the reason where you can see this particle is having energy close to average energy, correct, but it is not exactly the average energy. So there is distribution of energy. And how this distribution is happening? The distribution will happen based on the formula that is given by Boltzmann, where I am having Nj is the number of particles in energy level J, and I is the number of particle in energy level I, and this is equals to K exponential delta E divided by kb T, delta E divided by kb T. Delta E is the energy difference Ej minus of Ei, Ej minus Ei, correct? So this is the distribution. Yes, yes, obviously the entropy is something that has to be there and should increase. But then entropy of universe I am talking about, or entropy of isolated system, correct? So this is the concept that is there. So this is difference in the energy that I am saying, and this is the distribution of particle in different energies. Now I am just saying, okay, I have thousands of chocolates and I have a class of 50 students. I want to distribute the chocolates, right? What will happen? I have 1,000 chocolates and distributed to 50 students. I am plotting a distribution, right? Is it possible that one student will get all the 1,000 chocolates? No, right? Others will also collect. I am just throwing chocolates in class. I am throwing chocolates in class. Students are now collecting the chocolates. Is it possible that all students, one students will get all possible, or all the 1,000 chocolates? It's not possible. Similarly, it's not possible that all students will get zero chocolates, correct? That is also not possible. What will happen? 1,000 divided by 50, so it is 20. So 20 is the average number of chocolates that each student should get. But is it the case that all students should get 20 chocolates? No, some might get 19, some might get 18, some might get 22, right? So this is my average value, and around that this is the distribution. So you can see getting a 1,000 chocolates by all students is also not possible. Getting zero chocolates in all to all students is also not possible. So most of the students will get chocolates close to this, right? And for that distribution, this is how the probability will look like. So probability of happening that event. Similarly, energy, I have a system has particles, system has molecule, I want to distribute the energy. It is highly unlikely that all the particle will have zero energy. Similarly, it is highly unlikely that only all the particle will have the higher energy. And this distribution is something that maximizes the W. It's the most favorable. And how to get that W? In this W there is some distribution, right? Just like what we saw, for each distribution there is corresponding W. Here W was 3, then W was 6, right? We want that distribution which has highest number of W, right? Can we do opposite? That means, can I get the distribution for which the W is maximum, right? That distribution is given by this Boltzmann equation, right? Boltzmann distribution, where it says that delta is something that defines the distribution. For example, now I am at room temperature, so temperature is less, right? If I change ej, ej is greater than ei, right? So this is how levels are there and how molecules are distributed into these levels. Correct? Molecules are distributed. This is my ground state, ei equal to 0, and this is how it is going up. So as the difference between ej is the higher energy level and ei is the lesser energy level, that is the energy value corresponding to those level. As this difference increases, ej minus ei, if it is positive and it increases, what will happen? This value will be higher, delta E will be higher. That means this ratio will be higher. So exponential that ratio will be higher. So exponential of negative of that ratio will be lesser. That means if the difference increases, the probability of molecule to exhibit or to stay in that energy level is lesser. If this difference increases, probability of molecule to stay in that energy level decreases, correct, at a particular temperature. That means lesser energy levels are almost equally are more probable. That means most of the molecule will stay here and there will not be any equal distribution, just like what I said, right? But what happens if I increase the temperature? If I increase the temperature, that means even if the difference is higher, since the temperature is also higher, the ratio is less. The value of that ratio is less. Exponential to that value is also less. So exponential to minus of that value will be higher, right? That means when the temperature increases, even if delta E is higher, correct, Nj going into the higher energy level is possible. Going into the higher energy level is possible because of the temperature. So at higher temperature, particles will have energy, right? If I have more energy, I can go to any energy level. If I'm having lesser energy, I cannot go to the higher energy levels. This is what it is. So with increase in the temperature, more and more energy levels are also equally possible. To give you a real example, I have for example, water in this beaker. I am heating the system, right? Before heating, all the molecules will be in the lower energy states. That means molecule will slowly move, right? Will move slowly. As I increase the temperature, what will happen? They will get heat. That means they will get kinetic energy. That means they will be moving, right? So if they are getting more energy, that means they will move more. What you can say? They will move faster, right? They will move faster. That means the molecule which is here at the surface can go up, and the molecule which was at up will come bottom. So there is mixing that is happening. To clarify this, for example, I have oil and water at room temperature. Those are separated. If so, what will happen? Water will stay in its original energy level, oil will stay in its energy level. So for example, oil is having higher energy level, right? It is at top. Here it is having lesser energy. So going from water to oil is not possible. Just like going from I state to J state is not possible at normal temperature. What if I increase the temperature? If I increase the temperature, the mixing will happen. Oil molecules can go into the water, water can go into the oil, and because of which the energy levels are, since the molecules are having energy, they can move from one location to other, and that means they can go from this energy level to other energy level and from higher energy level to lesser energy level. That means the difference between two energy levels is less. Even if the differences are, the temperature is something that is controlling. So at higher energy level, that means if I increase the temperature, the energy levels can mix, the difference between those energy levels is lesser, and those energy levels are accessible and molecule can go into those states. Correct. So conclusion is at low temperature, that means oil and water at lower temperature, they will stay at their own energy levels. That means ej is less probable than ei. So this is higher energy level which is less probable. Molecules cannot go into one from one phase to other. At high temperature, the mixing can happen. Molecules from this state can go into the other state. So for example, this is my oil, this is my water. The exchange is not possible at high temperature. Ej and ei are most probably equally probable. That means probable. That means molecule can go from one energy level to other energy level. Because of higher temperature, higher energy, higher movement, molecule can go from one phase to other. This is what we observe in real life. This is just an analogy which can be used to understand the distribution of energy in molecules. Then there were some extreme cases that we saw when temperature is tending to zero and when temperature is tending to infinity. So when temperature is tending to zero, you can just put this value over here. Temperature is tending to zero, so this value will be infinity, right? E power infinity is infinite, e power minus infinity is zero. That means Ng divided by Ni is equals to zero. Ng divided by Ni is equals to zero. That means number of molecule in this higher energy state are zero. Lesser number of molecules are there, right? When temperature is tending to zero, that means which is having higher probability 1, and I will be having 1 probability, Nj will be having 0 probability. Means going into the higher energy level is not possible when temperature is going to when temperature is tending to 0, right? Again, to give you an analogy, Ni will be equal to 1, Nj is equal to 0. That means all the molecules will stay into the ground state. So for example, this is my ground state and this is my first state. All the molecule will stay into this energy state. Correct. The probability of going into other state is not possible. So if there is no exchange is happening, right, if there is no exchange is happening, all the molecule will stay at their own location, they will not move. If they will not move, that means there is only one way, there is only one way in which I can distribute the energy into the system, right? If I am having some higher energy, then what will happen? Molecule from here can go there, molecule from there can come here, right? So I can have distribution of energy. I can have 5 particle here, I can have 4 particle here, right? In some cases I may have 2 particle here, I may have, total is 9, right? So 7 particle here, I may have 7 particle here, I may have 2 particle here. So see, number of ways are there. How many ways are there to distribute 9 particles? 1, 2, 3, and there are n number of. I can have 1 particle here, 9 particle here, 9 particle here, 1 particle here. So I can distribute the energy. That means W is still there. How many W are there? W are infinity, close to very high value. I cannot calculate, but I will just say W is there. But if all the molecules are present here, then how many ways are there? I want all the 9 particles to be at the ground state. Then only one distribution is possible, that 0 molecule is here, 9 molecules are here. correct? So how many W's are there? W is equals to 1. Whenever temperature is tending to 0, that means temperature is equals to minus 273 Kelvin. W is equals to 1. What is entropy? Entropy is equals to kb ln W. What is W? W is equals to 1, right? Whenever the temperature is tending to 0, W is equals to 1. If W is equal to 1, ln of 1 is 0. That means entropy is equal to 0. That means at minus 273 Kelvin, when the temperature is equal to 0 degrees Celsius, no, it is at absolute 0, right? Minus 273 Kelvin. S is equals to 0. Correct. Okay. So at that temperature, you can see there is only one way that in which I can distribute the molecules. All will be in ground state. That means W is equal to 0. If W is equal to 0, entropy is equal to 0. That's why the third law says for an isolated system, right? At absolute 0, entropy is equals to 0. This is the validation for that. Then what will happen if temperature is tending to infinity? Then Nj will be equals to Nj divided by Ni will close to 1, right? Because temperature is infinity, 1 by infinity is 0, correct? E power 0 is equals to 1. That means Nj equals to Ni. Nj is equals to Ni, right? Here Nj is equals to Ni. Molecules in all the states are equally probable. Molecules in all the states are equally probable, and there is almost an equal distribution of molecules. So this is something that tells you probability can be used to understand the thermodynamics, right? Yes. And then we saw that there are two things that are essentially happening. I have an energy E, right? And there is distribution of energy. So next time onwards, if somebody is asking what is entropy, you can clearly say, okay, entropy is distribution of E among particles, right? Distribution of E among particles, and this is E. So there is a relation between E and S. E is the total energy, total number of chocolates, and how I'm dividing into the number of students, how I'm dividing into number of particles, right? That is giving you distribution, and that distribution is giving you S, which is equals to Kb ln W. Correct. Now if I change the E, what will happen? I will change the distribution. Correct. If I change the W, I'll change the distribution, and that means entropy will change. So if I'm having water in a beaker, it is a closed system, volume is constant, right? Water in a beaker, and I am heating here, correct? If I'm heating, then I'm adding Q. Addition of Q will change U, right? Q plus of W. If the energy changes, that means the distribution of energy will go and change. Therefore addition of heat into the system will lead to the change in entropy. So whenever I'm talking about addition of heat or removal of heat, it corresponds to change in entropy. Change in entropy, correct? Change in entropy. Similarly, if I am having this small system, if I have big system, then particle will be move will be apart. They have some disturbance, different energy distribution, right? So whenever I'm changing the volume, what is changing? The difference between energy level changes. So this is my delta E1, this is my delta E2. Correct? Difference between I and J when I am having bigger volume V2 and same smaller having smaller volume, that is right. So whenever I'm having lesser volume and whenever I'm having a bigger volume, what is happening? If I'm asking two students to stay in a room, right? To stay in a room, what will happen? They have very less space, so they cannot move around, right? So the energy difference between different states will be lesser. They can just go up to the door and they can come back. That is what is the distribution that is possible. But if I'm having those two students in a district, they can go to any other location, right? So the energy difference between two steps, energy distance between two energy levels will be higher. And if the energy levels are being changed, that means I am doing work onto the system. So addition of heat will change the entropy. And if I do work, because changing volume, if I want to change the volume, that means I will have to, if I change the volume, that means I will have to do the work. And if I do the work, that means energy difference between the energy levels changes. And if the difference between energy levels changes, that means that corresponds to work. That corresponds to work. Correct? So that's what we saw. Now the question is, if I add heat into the system, will the temperature change? If I add heat into the system, will the temperature change? Right? If I add heat into the system, will the temperature change? Without doing any calculations, for example, I have a cooker and again I'm using water. I'm heating the system. What will happen? If I'm adding heat into the system, earlier it was at 25 degrees Celsius, now the temperature will increase to 50 degrees Celsius. So what has happened? Addition of Q has changed the temperature. But will it happen every time? It may not, because, for example, if I keep on heating the system up to 100 degrees Celsius, the boiling of water will happen, and during that time, Even if I had add heat into the system, the boiling will only happen at 100 degrees Celsius, and there will be no change. The temperature of the system will be at. So you can see upon addition of heat, in one case there is change in temperature, and in another case there is no change in temperature. Can you prove it mathematically? Delta U is equals to Q plus W. Here, if I add heat into the system, right? For example, closed system, W is equal to 0, right? And delta U is equals to Q. And since it is constant volume, right? W is equal to 0, du is equal to cv dt is equals to dq, right? That means addition of heat will change the temperature. Addition of heat will change the temperature, correct? But in other cases, it may not happen. So whenever I'm adding heat into the system, as I say in micro scale that we are basically studying, will change the distribution of energy because I'm giving more energy to the system. That means I have more number of ways in which I can distribute the energy. That means I can, here what I'm doing, I am changing the entropy of the system. I'm changing the entropy of the system. But if I change work, that means if I do work on the system, in that case, the volume that is accessible that was given to the system particles will change, because of which energy level, the difference of energy between multiple levels will change, right? That will cause this no change of energy levels, change of energy levels, correct? Correct. So whenever I was talking about, for example, this system where it is a closed system, right? Number of particles are constant, volume is constant, temperature is constant, where there is exchange of energy. Exchange of energy means constant temperature, right? Volume is constant, number of particles are also constant. Mass is being exchanged, no, because it is a closed system. So if mass is not exchanging, that means mass is not exchanging, that means number of particles is equal to constant. So what I'm controlling, I'm controlling number of particles, I'm controlling volume, I'm controlling the temperature. So these are my natural variables or controlled variables, right? And what is the equation? We know that delta U is equals to Q plus W, right? Delta U is equals to TDS plus VDP, correct? Yeah, PDV, correct? This is for isolated system, correct? For isolated system. So for that, for the instant, please consider other system. For example, isolated system where there is no exchange of energy with the surrounding, no energy and mass exchange. If no energy is exchanged, right? If energy is not exchanged, that means energy is constant. We generally call U, right? Energy is constant. Then what else is constant? Volume is constant, right? Right? Volume is constant. Then the third thing that is constant is number of particles is constant, because it is a isolated system where there is no exchange of particles. No exchange of particles, N constant. No exchange of energy, E constant. So this system is NVE. In BTech we study isolated system. Here we are using a statistical mechanical approach to represent the same system, that is isolated system, using mathematics. And what are the controlled variables? Controlled variables are number of particles I am controlling, number of volume I am controlling, and energy I am controlling. That means this system in statistical mechanics is called as NVE or NVU system. We refer U and E interchangeably, right? So this system is NVE system. What are the controlled variables? Control variables are volume. Control variables are volume, energy, and number of particles. Correct? Right? So, in this equation, right? In this equation, what are my controlled variables? You can see here TDS is written. TDS is written. That means to evaluate this X quantity, for example, I need to write temperature as a function of S, right? Temperature as a function of S, correct? So S is my controlled variable, volume is controlled variable, right? Volume is controlled variable, and there will be also mu dn, where n is also controlled variable. Can I do other way around? Here, if I do, this is du, can I have ds is equals to du by t? Yes, du by t minus p by t, correct? Minus, this will go this side, minus p by t dv minus mu by t dn. What are the controlled variables here? U is my controlled variable, v is my controlled variable, and n is my controlled variable, right? That means number of particles are not changing, volume is not changing, energy is not changing. That means what is this system? We just defined NVE. So in this system, entropy is something that defines whether the process will happen or not. So keep in mind, whenever I am having an isolated system, I will be always working on entropy, because that will tell you whether the process will happen or not. Why? Because in isolated system I have NVE is constant. That means NVE are my controlled variables or natural variables, and this is what is being defined using this equation. This is what is being defined using this equation. Correct? So that's why this is my equation of state. This is my equation of state for, or instead of writing equation of state, we call it as fundamental equation for isolated system. For isolated system, this is the fundamental equation. Then we also have learned about, okay, what is called as Legendre transformation. Legendre transformation, just like, in a simple sense, I'll explain you, which will be easier for you to understand. If I am writing y is equals to mx plus c, slope y x, what is happening? I am representing the line using y is equal to mx plus c, correct? I have some data x, I have some data y. The same can be represented using, can I do one thing? M is equals to y by m, wait, y by m minus c by m is equals to no y minus c is equals to mx. So mx is equals to y minus c, m is equals to y by m plus of c by m, right? M is equals to minus c by m minus c by m plus y by m. What I did just now is I have represented y and x data in terms of m and x, m and slope and intercept. Now I am using slope and intercept to define a curve. To define a curve, right? That means this is my new y cap minus 1 by m is the m cap or m dash, c is my, and then y 1 by m. So you can see this is my y dash, this is my m dash, this is my x dash, and then rest of the thing is c dash, correct? So at each point there is some particular value of x, y and x pair is there, correct? So these points were represented using and intercept slope and intercept. I am doing opposite thing. I am representing this line in terms of the transform variable. That means I am writing in terms of slope and intercept. So here it is slope and intercept. So to define a line, to define this data, I am taking the help of slope and intercept. Correct? And as I said, this is my y dash, this is my x dash, and whenever I am now representing in transformed variable, what is my slope? Slope is this. Slope is minus 1 by m. That means this line should be like this. And intercept is what? Intercept is y by m. Correct? Y by m. Right? So to define a line which was in terms of x and y, now I am defining the line in terms of slope and intercept. What is the use of this? For example, if I am writing now du is equals to tds plus pdv, tds plus pdv, if I take this du divided by del s at constant volume, it is my temperature, correct? It is my temperature, and del u by del v at constant s is equals to pressure, correct? So this is my slope. I'll just write one thing so that it will be easier. This is my slope, this is my slope, right? So what we did, we had y is equals to mx plus c. So we change it to c is equals to y minus mx, right? So this is my, this value, this is my intercept, and this is my x value, new x. It can be represented as this also, it can be represented this, both are, both the ways are fine, correct? So can I represent this equation using the same? What is my y? Y is my s, correct? Because I am writing in terms of this, c is equals to y minus mx. So what is my y here? Because I am taking s and v, yeah, u and s. So this is my u, this is my s, and then whatever slope I am getting, du by ds, correct? What is my slope? Slope is du by ds, del u by del s. And what is my x? X is my s. It is equal to some quantity. For example, I am writing it as a any number, c, let it be c, correct? This is giving you s minus, what is this? Del u by del s is my t, this is s, uh, x is s, y is my u, sorry, it was a mistake here, this is u. See, this is my u, this is my s, that's why my slope is equals to del u by del s. So this is my u, this is u. Now what should we see? You know, u minus ts is the Helmholtz free energy, which is equals to f, right? Helmholtz free energy, which is equals to f, right? Therefore df is equals to d of u minus of ts, which is equals to du minus tds, and then minus sdt, correct? And what is du? Du is equal to tds plus pdv, minus of tds minus of sdt. This will get cancelled, pdv minus of sdt, pdv minus of sdt, correct? Right? So what has happened? This is equals to df. This is supposed to be minus pdv. This is equals to minus. So what I did now, just consider these two equation, equation 1 and equation 2. I use Legendre transformation. Earlier, what were my controlled variable? I was controlling entropy and volume, and my free energy was del u. Right now I am controlling temperature and volume, and my free energy is Helmholtz free energy. Similarly, one more transformation you can do for this. Right now I did for s and u. You can also do it for P and U, correct? P and U, this one, second term, that's what I wrote. Du by dv is equals to P, this one. And then you will get some quantity like minus of pdv, and it will be, you will get vdp minus s dt, and this you are going to get as dg. So now if you just look at these three equation, you will see in my system, if I am controlling s and u, then my change of that system from state 1 to state 2 will be decided based on the delta u value, right? I can write this again as ds is equals to du by t, and then p by t dv. That means if I am having energy as a controlled variable, volume as a controlled variable, which is my isolated system, right? This is my isolated system, that's what we had looked after here. So for that isolated system here, entropy will something that will give you whether whether the process is possible or not, right? But is it possible to control the energy of the system? It is difficult, right? Is it possible to control the entropy of the system? It is not possible, right? Then what is possible? Can you control, look at the equation 2, can you control temperature of the system? Yes, I can control the temperature. That's what we are doing. If I am having a bottle, inside that coke is there, I want to keep it at room temperature, I can control. If I want to keep at other temperature, I'll heat it and I'll stop the temperature if temperature reaches that value. That means I can control the temperature, I can also control the volume, right? In previous case, entropy was something that was difficult to control. I cannot measure entropy, so how can I control the entropy? But I can measure temperature and control it. I can measure the volume and I can control it. That means this system is NVT, correct? If it is not written, that means it is N is already there, right? So I'll write mu dn. So this is my NVT system. Number of particles are not changing, volume is not changing, temperature is not changing. What is this system is called as? This system is called as closed system. Closed system where there is exchange of energy, that therefore temperature is constant, where there is constant number of molecules. So this is my closed system, and that for that closed system I can define in terms of Helmholtz free energy. That means for this closed system, whether the system will go from state 1 to state B, it will be completely can be described using Helmholtz free energy. Helmholtz free energy. And why do we did these things? Because in first case it was difficult to control the entropy, but in second case it is easier to control the temperature. That's why we did reverse. Here it was entropy was controlling, here temperature is controlling. Again we can do one more transformation and see third equation. Temperature is controlling and pressure is controlling. We can control the pressure of the system. If I keep any bottle, a beaker containing water here at room temperature, temperature is constant, pressure is control, easy to control. If it is easy to control, then what is the free energy? It is the Gibbs free energy that will tell whether the system will go from system A to system B, correct? So here what is happening, pressure is constant, temperature is constant, so I have a piston cylinder sort of system that we have studied in 12th class, right? Some liquid is there, piston cylinder arrangement is there, where I am keeping the pressure constant, temperature constant. Number of molecules are not going outside the system, that means number of molecules are also constant. So this system is called as isothermal isobaric system. where pressure and temperature control is easy. And that's where in those systems delta G, that is gives free energy, will tell you the whether the process will happen or not. And all the reactions that we see in chemical engineering, chemistry, those we generally perform at room temperature and atmospheric pressure. That means temperature and pressure control is easy. And that's why we say that if delta G is greater than 0, then it is not possible. If delta G is less than 0, then what is happening, right? So it is the delta G that will tell you the system property. So depending on whether you have a closed system, whether you have open system, whether you have any other system, you can calculate the free energy. This is Helmholtz free energy or Gibbs free energy or entropy, correct, which will tell you the feasibility of any process. So now if now onwards, if somebody is asking for an isolated system, right, what is the free energy? Free energy is entropy. Universe that we have, this is what, this is an isolated system. So whether anything is happening, right, if something has to happen in this universe, what is something that will tell whether that process is feasible or not? It is the entropy which will tell you whether the process is feasible or not. If I am having a coke bottle right here in front of me, which is a closed system, right, this is a closed system. So will the temperature exchange with the surrounding, or if I'm shaking it and keeping it at some equilibrium, whether the process will happen or not, it will be dictated by the Helmholtz free energy, correct? And for a reaction which is happening at constant temperature and constant pressure, it is the Gibbs free energy that will tell whether the process will happen or not. So depending on my system under consideration, I will define my own free energy. And now it goes back to the 12th standard, why people were saying okay, delta G has to be something that will decide whether the process will happen or not. Here it comes from this. And here it is the advantage that we got from the Legendre transformation, where we are representing system using slope and intercept, instead of y and x, instead of y and x, correct? So this is my y, this is my x. If I want to represent, I was using my slope and intercept, correct? Slope and intercept. Now I am changing it into different form. Y is equals to mx plus c to y minus c is equals to mx. I am representing it using what? Slope and intercept. Earlier it was y and x, correct? So I changed from this to this, so that my control variable will change, and accordingly I will get the free energy of the system. So in the next class we will solve the assignment questions, and then we will also look after, okay, why entropy should keep on increase, whereas delta G should decrease, delta F should decrease, and what and all sort of free energies that we have, they should decrease and they should increase, correct? All these corresponds to the same. But then why we are saying this, that we will look after using some simple derivations, right? So and we'll solve some questions as I said. So if you have any doubts, you can ask, and upon that we can conclude the session for today. Yeah, so I'll be here. If you have any doubts, please let me know. Yeah, so if there are no doubts, we can close the session of the day. Thank you so much. We will meet next time in next week. Yes, yes, you are audible. Yeah, yeah. Mhm. Just a minute, I'll switch off. Yeah, yeah. So I removed one now. Hmm. Hmm. If it is closed system, then temperature. No, it is other way. The energy will exchange to keep the temperature constant. Yes, yes, yes. So there is exchange of. Uh, what you are saying is correct, but that will happen in transition. But once you reach an equilibrium, the temperature will be constant and energy will keep on exchange. Mhm. Fluctuations will be there, but it will fluctuate around a mean value. Yeah, yes. Mhm. Because when you do MD simulations, there you see that we calculate force, right? And force is the derivative of energy, right? Del dE by energy, correct? DE by dr. R is the position of particle. That is a position vector. So that is dE by dr. So there is delta E and there is delta R, right? And we are working in the system where our R, that is a position, is in angstrom, right? So even a small change in the distance will cause huge fluctuations in the E, no, the total value. Because of which, obviously, whenever you do any NPT simulations, the fluctuation in the pressure will be higher because force is equal to derivative of energy, and from that force you calculate the pressure. So even a small change in the dr value will cause huge fluctuation in the force. That means it will cause huge fluctuation in the pressure. That's why we see a lot of fluctuation since we are at angstrom scale. So it will be obviously will there. Yes. So do you want the reason when to use Helmholtz free energy? Yes. So whenever our system is NVT system, yes, I can show, but then just like what I said, there could be the problem of echo. Just a minute, I'll connect, rejoin. So now audible. Am I audible? Yeah. So I'll share. Yes. So whenever I'm having a closed system, right? Just like what I have showed here, closed system, where I'll just draw here. This is my closed system. Volume is constant, right? And then number of particles are constant because I'm not exchanging the particles. Then, since the energy is exchanging, temperature is constant, energy is here, n is constant, potential is- so these are called as conjugate variables. Volume is constant, that means pressure is. So this is my NVT system. NVT system. So for this system, if I want to write an equation, fundamental equation, that fundamental equation will have number of particles, volume, and temperature should be constant. So number of particles, as you see here, volume and temperature is constant. So for that closed system, Helmholtz free energy is something is whether the process will happen or not. So if I am having a closed system, then it is the Helmholtz free energy. Yeah. So yeah, so depending on the system that you are simulating on your computer, you can say okay, which free energy will tell you whether the spontaneity of the process. So if you simulate NPT, then it is gives free energy. If you simulate NVT, then it is Helmholtz free energy. And if you just simulate isolated system, then it is entropy. Yeah. So yeah, so that is. Yes, yes. So there will be classes every week on Tuesday. Yeah. Okay. Yeah. So okay. Mhm. Mhm. No, no, issues. It will be fine. So could you please introduce yourself and let me know the interest of taking this subject on NPTEL? Okay. Ah, okay. Nice. Mhm. Mhm. Good. Yes. Mhm. Yeah. Mhm. Yes. The course is very interesting, and I see that he's the only that deal in so much of detail about statistical mechanics and then molecular simulations. So when I started my journey, I also looked after his lectures, Professor Jam. Okay. Yeah. Mhm. Okay then. So let's meet.